All right. Cool. Welcome back. Today we have the pleasure to have Dr. McMedHacks again. He gave the last lecture. He gave the last workshop, introducing some more concepts in Pytorch, and today we'll actually build our first image classifier. So I'm going to start sharing my screen and get it started. 1 second. Perfect. Awesome. All right. So as I said, today we'll have Dr. McMedHacks with us again to talk about Pytorch and implementing your first image classifier. And land acknowledgement. If you do not know which land you're on, please go ahead and click that link. Our virtual event is based in Montreal, Quebec, which is the traditional territory of Kanakahaka, and its own land, which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse Indigenous peoples whose presence marks the territory on which people of the world now gather. We encourage you to learn and discuss about the history of the land on which you reside. Yeah, please mute yourself during the presentation at all times, and we have the Q&A session at the end. And as I mentioned last time, we're in the middle of summer school now in week 4, and today's session is on implementing your first image classifier, and then please go ahead and click our link to see the rest of the program. So actually, I didn't have that screenshot here, so let me just show you that. Show you this here. Because for those of you who are medical physicists, we have the APM conference happening starting this Saturday, which is why we actually don't have a seminar session this coming Saturday. So what's going to happen is that today is here, and then today, the next time in week 5, we'll skip this coming weekend, but the next one will happen on July 16th, which is where we'll have speakers from industry as well as regulatory agencies from Limbus AI and the FDA, as well as Philips. They'll talk a little bit about their experiences from the industry perspective, as well as the FDA regulatory perspective in implementation of deep learning softwares and so on. So yeah, so that's what's going to happen, not this weekend, but next weekend, next Saturday. Jose, do we have a tutorial this week?
No, not yet. Yeah.
Great. So I'll just go ahead and introduce our mentors for this week. Moin, you guys remember, if you were here with us before, that he was a mentor with us before, and Kian, well, I don't believe we have had him before, so please go ahead and Kian and Moin to introduce yourself again to our audience.
My name is Moin, as Eugene introduced me. I'm a master's student in computer science at the University of Saskatchewan, and I apply deep learning to my research. I'm in bioinformatics lab, and I try to use machine learning and deep learning in my own research. And actually, I am Keihan. We were the mentors last time, so Keihan was also here. So he's gonna introduce himself again, but anyway. So thank you.
Oh, sorry. Yeah, please go ahead, Kian, introduce yourself again.
Hello, I'm Kian. I'm a PhD student in computer science at the University of Saskatchewan. And usually I work on a computer vision application by applying deep learning methods to solve these type of tasks. And yeah, this is the second time that I am here. Last time I was here again, and hopefully we can have a good session together. Thanks.
Perfect. Thank you both very much. And now we'll have Dr. Mahiban with us to start talking about implementing our first image classifier. Please go ahead and start sharing your screen.
Thank you so much. So can you see my screen?
Yes.
Thank you for joining this session. I'm hoping that this session will have more interactive session. In last session, we talked about how we can define the data set, the data loader, the training loop, and we trained a small data set based on Pytorch for, I think it was for liver disorder detection based on some features that we got from the blood test. This session is related to implementing our image classifier. So we will use many of the concepts that we had in the previous session. Feel free to ask any question from the previous sessions, even if it is not handled by me, because the repetition helps that we understand every concept that we have. And as I said, we do not want to memorize things. We always look into the documentation, and repetition can help us to learn better. So for this session, I have decided to use the MNIST dataset, medical MNIST dataset. So the MNIST dataset is very famous because from the name, you can find out that this is minimal size for images. So let's go inside to that. The MNIST dataset, not medical MNIST, is famous in many of the papers because scientists and researchers, when they want to apply different architectures, when they want to experiment different things, they can use the MNIST dataset easily because of the size of the image. Basically, the size is 28 by 28. For this medical MNIST, we have 28 by 28 by 28 for 3D, for example, for some MRI images or some medical images that have third dimension. But the good point about MNIST, as I said, the size, that if you want to change something in the architecture, we don't need to care about how config the system, how powerful GPU, what powerful GPU are we using. So still MNIST data is being used in for showing that an algorithm is in a state of the art in a specific domain. And this is the reason that we choose that. Another reason that is we're using this medical MNIST dataset for this purpose is the dataset for Torch is already created, so we don't need to care about how we populate our data for this course. So we suppose that from the previous course, we know that how create a data, a class, inherit from the data set, and create get item and length function, override them. And we go through the architecture design and also training the model. And another reason is that we can change the data type. So I first start with the pathology data, and then because we want to see something from the data to see the classifier works or not, we can, for example, use pneumonia dataset and see if you want to change data, if you have different type of images, what changes we need to make inside the pipeline of a training deep neural network. So for installing MedMNIST, we need to install it from pip, and yeah, let's go one cell one by one, and I will run this. So it will install the packages and libraries that need to be load the medical MNIST data. So the next part is just loading some of the module. I will go through them when I'm talking about the usage of these imports. So as I said, we can have different data. One of the things that we have selected for now is the pathology data. For selecting the data, you can only come here and see what was the name of the data in top of the images, and you can type them. For example, I said path MNIST, so the path MNIST will bring me the pathology data. And if you don't know how to use these MNIST, the only thing we need to do is there are some examples here. So if you go to the example, there are examples about how we get started with this library. So some part of the code that I have in my Jupyter notebook is just copied and pasted from this part, because this is how we can get the data from that library. So I will go through them. The first thing is data flag, as I mentioned, and second one is we want to download data because we already don't have it yet. And we can define number of epochs that we want to train the model, the batch size, how many images we load using the data loader, and the learning rate. And using these functions, we are defining the number of classes, number of channels as input of the data, and also the get the data class. So let me run these two cells. And yeah, so the next part is, so we have now data class coming from the Python class of medical MNIST. And now we need to say download those data. And when you download that data, apply some sort of transformation, because images usually are loaded maybe in pillow format or maybe in NumPy format. You need to first convert them to tensor and then normalize them. So these transforms coming from the torch, so you can define any kind of transform. For example, if you want to do some sort of augmentation, stuff like that, you can add line to this sequential commands here. And for now, we don't want to use any augmentation. Maybe we will back to it. But only thing we want to do is after data is loaded, it comes to this transforms function, and we say convert it to tensor, which is conversion from any other format like NumPy or Pillow to torch tensor. Then we do normalize it using the Z-score normalization. We had the Z-score normalization implementation last session that we just subtract the values by the average and divided by a standard deviation. So this is the Gaussian normalization. So we have the data, and we say for training and test, we can split them. These functionality coming from the MedMNIST. So if we have different data, we have to care about how we want to split the data. And from this part, so we are now jumping to the torch. So like previous session, we need to define the data loader. And for data loader, we have two, one for training and one for test. And for training, we get the data from dataset training, and for test, we get from the test dataset. And for training, we are setting the batch size to 8. And for testing, we set to 1 because I have for loop. I will show at the end that for each data, we feed it to the system and get the output and calculate the accuracy and other metrics. And also for test data, we do not shuffle, but for training, we can do shuffling. So after doing that and showing the training data set, we will have, let me run it again. And we will have the information about the data. For example, data is now getting downloaded, and we will get how many classes we have in this kind of data. While it is loading, I can go to the next line. So the data set inside the MNIST medical has a montage that we can show the data in 20 by 20 tiles. So it just gives us a representation of how data is. And yeah, so now we have data downloaded, and we have different labels. For these data, suppose we have 9 different labels. They can be like background, debris, mucus, and smooth muscle, stuff like that. I'm not expertise in the pathologies, but for these examples, we just want to see how we can train the systems. Then maybe we can go to the pneumonia, and with pneumonia, we have at least a better visual representation, at least for me. And we know the number of training sample, number of validation, number of tests, and we didn't get the validation. We only get the train and test for our cases, but we can get the validation too. And yeah, so this is the way that we load the data. So before we jump to the next part, so if we don't want to use the MNIST medical, and the way that we need to load the data is only implement this data class by ourselves. So we need to create that class inherit from the dataset class of Torch. And in initialization function, we need to load or get fetched all of the image list. And in get item, we need to implement the loading functionality. I will try to give just example after we finish this and also finish the pneumonia dataset. So now it's time to jump to the designing architecture and module. For architecture, if you remember from the previous session, we need to define a class inherits from NN module, and we need to override the forward function. And the Pytorch will figure out the backward loop using the graph it's created. So for forward loop, what I have created here is sequential layers. Some sequential layers, I call them convolutional model. And after getting after passing the image from some convolution layers, we have a classification layer. So if I want to explain it better, so we have an image here, and we have some convolution layers here. I'm not good in drawing, but I'm trying to show that this is coming to do through these layers, maybe 5 or 6 convolution layers. And after that, we have another layer, usually our linear layers and some activation function, and we have our classification layers. So this is the whole architecture that we can have. We can change it to a different way, like if you want to use, for example, the combination of transformers and convolution, maybe we have some sort of feature extraction, some specific layers of feature extraction. So we can design it as varied as possible. But for this case, I'm just using a simple architectures. The things that we need to care about is some parameters that we are using here. And we need to know how these convolution layers work. So for example, I'm saying the input image should come to the system and the input channels should be 3. So I'm supposing that we are feeding a RGB image to the system. So if you are feeding a grayscale image, or maybe your number of channel of images higher, for example, you are passing a depth or stuff like that. So you need to take care of the number of input channels you are passing to the network. And it said that input channels is 3 and output channel is 8 and kernel size is 3. So by this, we means that if you have an image, so we apply a kernel in size 3 by 3. Let me select something better like this one. Yeah. So this is image, and we are applying a kernel with size 3 by 3. So suppose that this is this is suppose this is 3 by 3, and we have 3 channel as input. So when we say 3 channel, it means that we, for example, we have R, we have G, and we have B, and we have this kernel. It's sliding on these images And we have output channel as 8. So we have 8 different channels. So we are increasing the channel dimension or third dimension of the images. So by doing that, if you see the next layer also, we are getting number 8 as input. So I'm just trying to plot some of these. So this, for example, this is the output of the convolution that we have. So we have, for example, 8 different 1, 2, 3, 4, 5, 6, 7, and 8. So we are getting an image, applying a kernel convolution, and getting 8 different channels. So we are increasing the number of features that we can get from the image. One of the purpose of doing that is when we increase the number of channels, we are specifying, for example, one channel should focus on specific features, because this kernel for creating this channel, maybe it's initialized by some weights that, for example, is sensitive to extracting edges. Maybe another kernel is we are creating for creating the second channel. It's more focused on extracting edges in a specific direction. Maybe another kernel is specific to extracting some texture, not edges. So we are creating some layers that each one is focusing on specific features, and we continue doing that so that for the next layer, we will have input 8. We should have input 8 because we already have 8. And we are increasing that again to 16. And we continue that to get to 32. And the kernel size we have selected is 3. If we want to have a bigger or maybe looking to the more general features rather than the local, maybe we can increase the kernel size, or maybe we add dilation. I will go through that when we go to the convolution two-dimensional documentation. But this is the main idea that we want to get as much as feature as we can. And between each layer, we have activation function and also the max pooling. So let me bring the convolution two-dimension. As I said, maybe this is our first time that we are using convolution. Maybe our domain of expertise is in audio. We usually use one-dimensional convolution, and this is our first time we want to use convolution in two-dimension. And we can go to the Pytorch documentation and see how it is and what parameters we can pass in order to have a better flexibility of changing the algorithm. So it said that we need to pass number of input channel, number of output channel, the kernel size as we defined, the stride and padding, and dilation. I want to talk about these different stuff here that are important for our cases. So we have here dimension for dilation. There is a link. If you click in the link, they are showing good animation that how these different things like padding, the stride, and dilation works. So this is an example that we don't have any padding, we don't have any stride, and what we are doing is just sliding the kernel on image, and you see that kernel is first in 3x3, then just moving 1, and we are creating 2x2 as the output. But if you have padding, we still don't have a stride. For example, we add 2 different padding because we want to create an image or the output as same size as the input that we have, or maybe we want to get it something bigger. So for example, here we add 2 padding. Usually padding is set to 0, and when we want to sliding the window, we slide it somehow to cover all of the padding that we have. So these centers values are same when we don't use padding, but we have some other values here that can be used. Especially this special when we are more careful about the edge and corner of the images. Another thing that we can do is we change the number of padding. Like this was 2, we can reduce it to 1. And what else we can do is we add a stride. So by adding a stride, you can see that we are skipping, for example, this is a stride 1, and we are skipping 1 pixel when we are moving the window. So we get this kernel over the image, and then when we want to move that, we just skip 1 pixel and go to the next window, next sliding window. And one of the other things I just want to bring here is a dilation. So if we increase dilation, it means that when we want to apply the kernel is not a concrete matrix. It has some skipping connection here. So you can see that the kernel is not 3 by 3, it is like 6 by 6, but we do not compute for example, for here, we do not compute for even numbers or odd numbers. So this gives us the opportunity to have a bigger region of interest. So it's being used when we want to have global features from the image, but it will reduce our attention toward the local features because we are losing some of the information when we are focusing on a small part of the image. And using the dilation mainly is used in papers like WaveNet, stuff like that, that people want to have a better global features from signals or the images. And for this case, we can use all of these kind of approaches if you want. For example, if we want to use dilation, we can have a better global features from the images. So let's back to the what we have. So we have rectified linear unit function, and after that we have max pooling. I think there was some images also about that. So the max pooling is like the sampling or downsizing the image that we have. So after we get the output of the convolution, we can use by kernel size, for example, 2, and between each 2 by 2 windows, we get the maximum because we are using the max pool. We can use, for example, average pool. So we get the maximum numbers in that 2 by 2 matrix. So let me give you an example. For example, we can say if you don't know how max pool works, maybe we can bring the we can bring 1 images. So maybe this is good. So suppose this is the output of the convolution. By applying the max pool by kernel size 2, it is exactly this. So we have 20, 12, 8, 12, and the maximum number in this 2 by 2 is 20. That's why 20 is selected. And for this one, the 30 is the maximum. We select 30. So it is like the downsizing the images. And because we are using stride 2, it's like we do not downsizing the images because we keep some of the pixels or values from the outputs, and we just select some of the highest value of features for the next layers. So this is the overall architecture of the convolution. We can do many things here, as I said. So we will try to come back here if we want to change the architecture. The next part is getting the classification. Now we have some features from the max pooling 2-dimension here, and the size of the feature is based on the number of output channels that we have. And we say, get this number of features and give us 16 features. So now we want to downsize the number of features because we want to decide based on these features that we have created. So maybe we have, for example, 256 by 256 image. And now after feature extraction, maybe we have 2056 different features. And from these 2056 features, we want to decide that this image is belong to which classes. Maybe we have 9 classes for this data set that we had 9 classes. Let's back to here. So we had up to number 8 from starting from 0. So we have 9 different classes. So we have to downsize these features somehow using dense layers, linear layers, and we say the output can be 9 different neurons, and which neurons is getting the higher value. We suppose that the class related to that image is that specific class. Let me give you an example. So for example, as I said, we have the convolution layer. This is our convolutions, and we have our classifier. And for classifier, we are trying to downsize it to a specific number of layers. And suppose here, as an output, we have 9 different neurons. So we have 9 different neurons. 1, 2, 3, 4, 5, 6, and this is just for an example. Okay, so suppose that the images that we are feeding to the system is related to, let me see the classes, related to, for example, debris, or maybe, debris, number 3. So if we say this is, number 0, 1, 2, 3, so we suppose that these 3, that number 4s of the neuron should get the higher value when we want to classify the images. So we are supposing that this cell is getting the higher value. And I just want to show you 2 different things. These output layers here is called, yeah, go ahead.
Sorry, that was just someone that unmuted. Go ahead.
Oh, okay. So there is a question that is asked, that how do you choose the number of input and output channels for convolution? Is it a coincidence that is a multiply of 2? So there are different researches happening or happened before to find out what is the optimal number of layers that we want to define. So if you see some papers like efficient net, there are some rules when we want to define an efficient network, but basically it is arbitrary. You can select any number of input and number of output layers that you want, but if you want to do it efficient, you should follow some of the rules that, for example, efficient net architecture is designing. If you find the paper, you can share. We can go through it after the meeting. But efficient net is getting in some period, it was getting a state-of-the-art result based on just selecting appropriate number of output channels and number of the kernel size and stuff like that. And also there are some architectural optimization algorithm that it's not training the model end-to-end, it's just training for some epochs and using some sort of optimization, maybe grid search or storm optimization, it will try to fine-tune the architecture. So the neural architecture search, also the efficient net are ways for selecting these values. So let's back to what we are talking here. So we have the convolution layer and we have the classification, and this is the output of classification. This is called logits. This is important terms to know, because you may see it in many papers or maybe many discussions. And logits are the unnormalized outputs. So when we say, for example, we need number 4s for a specific image be higher, or all of them, we wanna have them 0, but this one we wanna get 1, and for all others we get 0. So it means that this image is corresponding to class number 4. I'm saying 4 because it's starting from 0, and but this is logits and they are not normalized. So we may, because we are using linear layer and we are not using linear layer, where we are not using any activation layer after that, we can get any numbers. So what we usually do is normalizing it. And by normalizing it, we can use log softmax, we can use softmax. So by applying softmax, we are somehow normalizing these based on the other values. And we are sure that the output range is somehow controlled, that if you want to do some sort of calibration, stuff like that, that is very important. One of the things also is important is the calibration, because we know that, for example, this image is selected as the predicted class, but we don't know, for example, with what confidence we are saying that this images belong to that class. So by normalizing that, we are getting some probability. We can see them as probability. It is not real probability, but for example, if we normalize them and we say this is 0.1, this is 0.1, and because we normalize it, maybe this is 0.92, higher than other cells. So we can say by about 92%, this image is belong to the class that we want. But still, as I said, this is not certain, because the value we are interpreting here is not exactly probability. They are logits, and we just normalize them. So there are some papers talking about how we convert logits to confidence. And if you see, for example, papers like calibration probability for regression, or calibration in deep learning, or calibration on black box, or stuff like that, there are many recent papers are coming how we can fine-tune these outputs to give us a better certainty of the classes. So there are two things here. First is the class value, class numbers, and also the probability. And these two are different. So let's back to the architecture that we have. We have the linear layer, and we get the logits from here. As I said, we need to normalize it using softmax. So let's go to the forward function, and I applied the softmax here. So close that. So when we apply the forward layer, we get the image and we pass it through the convolution layer. One of the other things that we didn't discuss is this sequential. So if you have multiple layers, and we want to just name it as something like here as convolution model, we can use sequential layer because they are applying the data through the pipeline using sequential behavior. And if you search also for documentation in sequential, it will show some of the other function that we can use. Maybe we want to use hooks or stuff like that inside it. And but for our case, maybe if we don't want to use sequential, we need to define each layers. Like I can say self.convolution first layer. For the second one, like the previous session, if you remember, for the first one, we need to again define it to the variable like activation layer 1, max pooling layer 1, or stuff like that, or define a general max pooling because max pooling doesn't have any weights. And we apply, when we want to apply the forward function, we have to do all of the things again. We pass the model through all of the variable that we define. But here it's very simple because we use the sequential model. We pass the input through the convolution, so we get our outputs and features. Now the output and features get flattened because we have, as an output, we have 32 different channels. And when we flatten, we are just making them a one-dimensional array. And by applying that one-dimensional array to the classification, because we have linear layer here, we get the logits. And now this is logits. Let me actually change this, maybe that's better. So we get the logits and we pass the logits through the log softmax and we get the output. And now we can get the output and also get the logit. So that depends on, as I said, we have logit and also we have the output. That depends on which one we want. We want to normalize one, or we want the unnormalized one. So for training the network, we can also use the logit without normalizing it. But if you want to get the certainty or confidence, or even we can return the output for training also. But if you want to focus on the certainty and confidence, which is very important, especially in medical purposes, we can define a new output, work on it, calibrate it, and then return it. That's why I just separated. So other things that we have here in initialization is the optimization. That this time we are using Adam. In the previous session, the default function was a stochastic gradient descent. And for Adam, we set the learning rate to 0.001, and this self.parameters is just returning what parameters of networks can be trained. And for loss, we are using the cross entropy loss. And as I said before, we can also change this, for example, to KL divergence loss or any other loss that defined for classification. So now we have med-means model. So this is called, this class called med-means model. And now one of the important things that differ from the previous course is that for training images, it's better to use GPU because you know, we have 256 or maybe 28 by 28 in this, even in this example that it is tiny, but 28 by 28 is lots of features comparing to previous session that we only have like 4 features. So we need to have GPU for faster training and experimenting better. So I think there are some questions before going to the next. Oh, thank you. Yeah, for efficient net, so we can walk through it after. So let's back to the model. So we can say for selecting between the GPU and CPU, one of the things that we can use is using this if-else condition, that if GPU is available, it will automatically select the GPU. If it is not, it will automatically select CPU. Because as you know, that in Torch, we can say that is CODA available, and if it is, we set the device to CODA. And because we only have one GPU, we set the CODA 0. If we have more than GPU, so we can say, for example, CODA 0, 1, 2, and how many number of GPU that we have. And one of the other functions that we have is model 2, and we say to the device, for example, if the device is CODA, so the model and its weight will be copied from the CPU to the GPU. And if it is CPU, so if it was on the CPU, it will not do anything for us. So using this like model to device and also using data to device, so like tensor to device, will copy the information from the CPU to the GPU. And sometimes this is time consuming. So if it is an image with high resolution, or if it is a model with like 1 billion parameters, maybe just this line takes some second to be done. It depends on your system. But I'm just saying that if you have these kind of things in your training loop, be careful that you do it efficiently. So one of the things that we need to be sure is that we go to the edit and in the notebook setting and select the GPU as a hardware, because if we do not do it, it's automatically use the CPU. I already select that, so let me run this also again. So it said that we have CODA available, and because I have print the device, now it's copying the model to the GPU and also printing the model. So now we can go to the main loop of training. So we have defined the number of epochs above, and you remember this kind of loop that we have on the data loader from previous session. And if you don't remember, please ask. When we go through it, the repetition can help us to understand it better. So we have a data loader, training data loader, So we have a for loop over it, and we get the data, and we get the target. And we pass the image to the model. I call it images because we have batch size of 3, I guess. We defined it here on the top. So we have batch size 8. Yeah, we have batch size 8. So we loading 8 different images in each for loop that we are passing here. And we pass those 8 images to the model, and we get 8 different outputs. And we use the model criterion because we define the criterion here, the loss that we have defined here. So we pass the outputs and the target through the model. And after that, we get the loss. And by getting the loss, we need to go through the training loop of the torch. So we need to set the optimizer to 0 grad. Loss should be backward through the graph. And we pass optimizer 1 step to train the weights for 1 step. And what other thing that I'm doing here, just for showing the loss. Also, I just to remind you that I changed the notebook of previous session, and I added the loss and plotted for you. So if you want to track the loss in the previous session Jupyter notebook, you can do it. Also here, I'm not plotting it, but I'm just printing it to see that loss is decreasing, and at least we know that we have some sort of training. We cannot check again yet the overfitting, stuff like that. We will check that. We will implement it together. So so we have the running loss starting from 0 for each epoch. We get the loss, and we piling up using the loss of each data that we have in the training data loader. And for example, I say after each 2000 iteration, we just print that loss and we normalize it using those number of iteration, and we set it to 0 again. So let me run this and see how loss is changing, or if there is any problem. So while it is running, we have another part related to prediction. So we have another data. So you see that this is training, and each print line is showing 2000 different epochs, 2000 different iteration, not epochs. And so the good point is that the loss is reducing, and while it's running, we can go to the next part. So we have the predictions, and we want to get the predictions. And for getting the predictions, if you remember, we had the number of batch size to 1. And one of the other things that we need to care about is we don't want to save all of the graphs every time that we pass something to the model. I think it is already covered, but just repeating that again, because it's very important that if we do not use like torch nograds and also model.evaluate, if you have some sort of dropping layer, drop out layer, stuff like that. So it will not be, it will not eliminate those layers and also eliminate the graph that we have. So we loop through the data loader, and again, we get the image and target. And this time, when we have the model pass through the system, and I'm just using CPU for inference because the size of the images is small. And the thing is, after passing the model to the passing the images to the model, when we get the output of logits, we pass it to the CPU, and we do the argmax, because as I explained before, we have, for example, 9 different cells and neurons as output, and the maximum, the index of the maximum is showing the class numbers that we want. That's why we can say, give me the argmax of the output layers, and it can be applied even before applying the softmax. And we detach it from the graph and also convert it to NumPy. Because we are using torch.nograds, it doesn't need to be detached, but we detach it because we want to apply the argmax on something, and sorry, we want to apply it on, we want to convert it to NumPy, and we don't want to have any other dependency when we want to get the output. So we get the predicted, and we have the targets and predictions. Now we can use like the confusion matrix, the accuracy score, stuff like that. One of the other things that we need to do after training each model is to save it. So we can say torch.save, and we get the model statistics. So it will give us all of the weights that is already trained, and we say the path that model need to be saved, and we save it. And for loading, we can do the same. We can say torch.load, and we just pass the model path. So for getting the accuracy and the other things, so we can say we have the accuracy score. Like before, you can define the F1 score, you can define AUC score, stuff like that. And also another thing I bring here is the confusion matrix that we can see. For confusion matrix, again, we need to just pass the target and predicted, and we get the confusion. And using the Seaborn library, we can plot the heat map or confusion matrix, and that's it. So while the model is training, I think maybe the model is not training on GPU because I think it's a little slow. That's why I want to stop it, restart my kernel again. Be sure that this is running on GPU, because I think I previously saved it and I run it, and I could run it on the faster way. I think it's not on GPU. So let's run it from scratch. Because the size of the images are small, we don't expect that the training take long time, and that was the main reason that I just choose a small size of images that we can do different experiments. So while it's loading and when we put it on terrain, we can work on other parts. Like if you want to use, for example, different architectures, or maybe we want to change it to something else in terms of data. We want to use maybe pneumonia data set. So we can work on those parts. So there are some questions. Yeah, very good point. That if we use cross entropy loss, we don't need to use log softmax since it's already implemented. And it said also, after you flatten the output, doesn't it also change the input feature for the first linear layer in your classification model block? Okay, so for using the cross entropy loss, you don't need to using the log softmax, but even if you are using cross entropy loss, if you get the confidence, you get the correct confidence, you need to define the log softmax or softmax to just normalize them. But for training, you don't need to define them, because the cross entropy loss can work on different dimension range. And for the second, after you flatten the output, doesn't it also change the input feature for the first linear layer in your classification model? I didn't catch your point. So when we flatten this, so we are flattening this one because you know, we have how many output channel number of 32 number of output channels. And when we flatten this, and because we are using the max pooling layer also, assuming that we are not increasing the number of input after flattening that. So if we have 32 input feature, it means that we have, after flattening, the model is designed somehow that we only have 32 neurons. We do not have more than that. If I change any parameters here, the model will be break because number of input and output should be designed carefully to output of each layer match the input of the next layer. So yeah, I expected higher speed for training, but let's wait until it's done. Also, we can stop at any time because the model is under training. And if we stop it, for example, in this step, the good point about writing this kind of for loop is that the information is is saved in the model, and we can use it for prediction, but with the loss that we reach to it. Another question that is asked is, what if the hyperparameter are kept in such a way that output of each convolution layer have the same shape, but feature extraction is there? Then how this will affect the prediction? So by same shape, if you means that exactly like 3 channels, the same number of images, maybe that works. That depends on the data, but usually what we do, what we like to do is to increase the dimension of the images to get better features from the image. For example, if you are using encoder, we are doing downward, so we are trying to decrease, or better say, we are increasing the spatial dimension to get the better local features, or the features, the powerful feature that we can extract. If we wanna keep it as is, it's like, for example, it's like using, suppose we have a Gabor feature, and we are just using 3 different kernels for the Gabor feature. So if we are not increasing the power as much as we can. So that depends on the network. Maybe for some data that works, but if it is not enough, we have to increase the number of layers. So so you can keep it for training. It is 6. What number of epochs I put is, I think, is okay. It's 3 number of epochs. So, oh, I override it here as 10, so it should be finished in 10. So while it's running, I would just want to say something about the computer vision domain. That so it can be categorized in different parts. For example, we have image classification, we have object detection, we have the instance segmentation, we have the next session that we have is with me is UNet, which is semantic segmentation. Also, we have panoptic segmentation. So these are kind of things that we can do in computer vision. There are more, but for like starting in the computer vision field, you need to know what's the difference between object detection and instance segmentation, and also difference between instance segmentation and the semantic segmentation and panoptic segmentation, and also what's the difference between the classification and segmentation. So if you see here, the output that we are trying to convert the model from the features that we have is like flattened and then converted to the classification. So we call it classification head. but maybe we want to extract something else from image. Maybe we want to extract some position or maybe bounding box from the image to extract region of interest. So we may have another head connected to the convolution model, and we use it for just extracting some bounding box or some objects. So having a better flexibility and control on designing model give you opportunity to design different downstream tasks. So I think it's finished. Just one epoch remind, I guess. So you see that the loss is decreased from 1.5 to something like 0.5, which is good. But one of the things that we need to take care of is the overfitting, underfitting, and stuff like that. And when we see the accuracy loss is one of the way that we check the overfitting. And another thing is the defining the validation data set here. And in this for loop, when we go through the training data loader, we load the validation data, pass it through the model exactly like this with torch no grad, because in that for loop, we don't want to apply any grad and gradient on the validation or test data. And we just print the loss for the validation. Okay, cool. So this is run. So now we can go to the next part and use the model, which is already trained for predicting on the test data set. It's done. So now we can save the model just to be sure that model is safe if you want to use it in the future. And this is for confusion matrix. So we see that we could get about 78% accuracy on that data, which is good. We could, I think, based on the trend that we had, maybe we could keep it running for longer time and also set the learning rate to something smaller, because maybe after some, or maybe we have some learning schedule, for example, starting from same learning rate, and after a specific point, we want to decrease learning rate by some factor, because I see here maybe this is harder for the model to be trained. And but for now, it seems good. And using confusion matrix, you can see, for example, for class 0, we have some errors, like we predicted class number 4 as number 0. And if we go up just to see what was the classes that we have. So class number 4, which is 3 here, is lymphocyte, and 0 is adipose. So these kind of understanding, if we show some of these images, if we are expert in pathologies, maybe we can find out that why model has difficulties for detecting those kind of classes, and maybe we can change the architecture somehow that it is more focused on those kind of features. So now let's change the data to something that is more feasible for us, the pneumonia. The way I'm saying that, because it's a chest X-ray, and using chest X-ray, maybe we can see some field in it. So I change data to pneumonia, and I do the same things for loading the data. And also we want to see what challenges we have when we want to change the data. Oh, I have to load it from top. Okay, since it's downloaded, and if I show you some of the examples, so we can see chest X-rays, and let me see how we can get some of the data that are not and that are normal, and some of the data that are not normal. So we have the training data set, and also we have defined the data loader here. Yeah, just just for examples that we want to do that is we can loop through the terrain data loader, and when we get the data, I think we can say this is images, and also we can say we have targets. And if you see the labels, it's just normal and pneumonia, so we only have 2 different labels. And I just want to show you for one example. I don't want to print lots of stuff here. So I can, from matplotlib.pyplot, import I think there is imshow also. Yeah. So what I want to do is just if we have target like 0, we can print them. If we have target 1, we can imshow them, and also imshow the other images, just to see what is the difference between these two. Just for an example, let me show you what we have in images before going to that. So we have images. If you get the shape, we have 8, and 1 is the number of channels that we have, and 28 by 28. So the size of the image is 28 by 28 when you have 8 different images, because we selected 8 different batches in top. So for getting one of the images, what I can do is I can say I just want to get image number 0 from 8 different batches, and I call it image. And for target, what we have is just a list of values here. So 0, as I said, is like normal, and 1 is pneumonia. So if I just select number 0 and number 1, and I can say this is image normal, and number 1 is image with pneumonia. So I can say image pneumonia. And just want to show you that how it is look like. And also this is in Torch. Usually in some of the network, we usually put the number of channels at first, but in NumPy is in reverse. We have number of channels as our output, but because this is grayscale image, it doesn't matter. So you can only say that print the channel 0, or show the channel 0. So, and also we want to do that in CMap in grayscale. And you know, the quality of images is not that good to compare them, but let me just show you to how we can do that if you want. So it's not really usable for just interpreting in visual way, but if you have some sort of images that can be interpreted better, you can use that. Maybe I can reduce the size somehow. So for example, in imshow, I think I can pass size of the image. Yeah, I can. Yeah, I can create the figure, subplot, and also create size for them. Yeah, that would be better. I can, in that case, I can plot them together. And also for fixed size, I think, because I usually use the PyCharm, so I'm not sure that the subplot is here. Yeah, it seems here. Yeah, I try to decrease the size, but still, because the size of the image is just 28 by 28, maybe it's not useful. But just for your case, that if you have other image, you can just visualize them as one of the steps that's very important. So let's back and see what other changes we need to do when we want to train this system, because these images are different than previous one. The previous one was RGB images, so that's why we have 3 different channels. So let's see if I don't change what errors I get. So maybe by looking at those errors, I will try to fix that. So it said weight of size 8333, expected input 8, 1, 28, 28 to have 3 channels, but got 1 channel. So this is the main things that we had. The previous data had 3 channels because it was RGB. Now we have 1 channel, so we can pass 1 here. So if I fix that and again run this, so it seems that maybe there is no other issue. So one of the other point that I just saw to mention here is there are some articles and reports that say if we put a number of channels as last layer, it would be better in terms of performance and GPU. But when we put it in the first layer, like what we have done in Torch here, sometimes it's not good because in terms of GPU memory allocation and the pointer inside the GPU memory to point to the correct section of the RAM, GPU RAM, sometimes it's slower. So let's reduce this. For example, every 20 data, I want to just print a loss. Okay, seems that the loss is starting from even 0 because I think we are, yeah, maybe something is wrong. So we should check that, for example, this is one of the cases that we need to be sure that everything is right or not. So it's starting from 0.01. If we look at the accuracy after the model is trained, maybe we can see that if it is really trained or if it is not really trainable, because the resolution of image is too low. So we have this, and let's see the accuracy. Oh, cool. So we have 90% accuracy. Seems the data is very easy to train. And we have about 90% accuracy in detecting pneumonia from those kind of image resolution, which is hardly to see by naked eyes. So there are some other questions. Okay, thank you, Kehan. Yeah, my concentration about the using the output, the logits of the network and also the softmax layers was to highlight this fact that the output that we are getting supposed to be probability, but they are not probability. If you search for some of the paper like calibration probability, there are some papers recently about, especially in clinical decision making and medical approaches. So we need to be sure that the calibration probability is not same as the logits and the normalized logit that we have. So usually people for calibration do some sort of another layer, put another layer after the logits and have a calibration set for training, calibration set for testing, and calibrate the last layer for probability on calibration train set and test set on calibration test set. I think in scikit-learn also we have calibration probability if you do not search for the paper. Yeah, here we have some sort of calibration probability, for example, for SVM, random forest, stuff like that. We also have for deep learning, because deep learning is also new for this area. So the output, the logits after passing to the softmax, it's important to convert them somehow to usually have very close value to 0 and 1. We don't like shape like this, because in these shapes, if one small change in the networks happen, or maybe input image has a small noise, so we are changing the output from class 0 to class 1 for a binary classification. But for this kind of system, even a small noise, or even sometimes highly noisy image, cannot make the problem for the system for diagnostic. In this kind of calibration curves, after passing the logic through some sort of normalization and also some sort of calibration, we have some sort of this calibration curve, which means most of the image are predicted with very low probability or with very high probability, because we are sure about something or we are not sure about something. We should not say, for example, I know that 60% of the time, or maybe with probability of 60%, this person has some sort of disease and disorder. It's better to say that with 90%, I'm saying this, and I'm not sure at all about this prediction. So yeah, that was the reason I just bring this up. But just for training, even if you apply the log softmax and apply the cross entropy, I think because it's already implemented, it doesn't matter. So yeah, so we have trained with two different things. We can change the data set and play with this algorithm, and also we can change the architecture as we want. So for example, in recent years, that most of the approaches are based on like combination of transformers, attention layers, and also the convolution. So we can apply some sort of feature extraction using convolution, then having some sort of transformer here, and then we have the classification head here. So the different things can be applied here. I hope that I covered most of the things that need to be. Please feel free to ask any question.
Thank you very much. So anyone who have any questions, please go ahead. Start asking questions. If not at the moment, maybe we can go back to the first question that we had, which is how to find how do you choose a number of input and output channels for convolution. You mentioned the efficient net, but how, like when you do this yourself, if you don't rely on efficient net, what's the logic that for you to choose the numbers that you just did in the Google Colab? And then maybe we can go through efficient net afterwards.
Yeah, sure. So what we usually do is to increase the number of spatial increase the number of channels that we have, and decrease the number of spatial dimensions. So the reason for that is for each different channel, as I said, we want to focus on specific features, and if we increase these number of channels, we are increasing our power for detecting different kind of texture, different kind of edges. For example, one I can give you just in terms of image processing. So if you have like Sobel filter, like this one, so maybe after training, during training the model, one of the kernel for creating one of the channel is selected like this. So it is only sensitive to vertical edges. Another kernel is defined based on this one. So it is sensitive to the horizontal edges. Maybe another filter is defined not sensitive to edges, but sensitive to different specific texture on the images. So if we increase these numbers in the middle, so we are increasing our power in extracting more features, more variety of features. And we usually do that because we want to decrease the resolution of the image, but increase the dimension of the feature that we want to extract. So usually something in power multiplied by 2, for example, if you have 8, we get 16 and we get 32. That works. But if you see some of the papers, sometimes there are not specific rules. Sometimes based on the power of the system they had, or maybe based on how many features that they want to extract. They, for example, I can say after these 16, I have a convolution just with 1 point. I mean, with output of 1 channel, and I just want to convert it to something like semantic segmentation, for example. So that depends on the downstream task. That depends on the power that you have for training the system. And yeah, that's it. But the better is to follow some rules that showing based on trial and error, better accuracy and performance. So if you want to go to the efficient net, so the efficient net, if you see in the years of 2020, it could get the state of the art in comparing to other architecture like ResNet or stuff like that. So one of the rules they mentioned, if you see here, so they said that if you have a baseline, so one of the approaches that we can do is we do width scaling. So in each layer, we try to increase the spatial dimension. Another approach is to depth scaling. So we increase the depth of the network. And another one is the resolution scaling. So when we apply the image to the network, we try to increase the spatial dimension, and also the network size and network depth is a little higher. But there are some rule of thumbs here. They mentioned, I think, in the here. So they said that if you read this paper, it said usually the width and depth and resolution in each layer can be defined using this formulation, and this will give us the better performance and accuracy. Yeah, I think the whole paper can be only summarized in this formulation. If we read from they also mentioned that the alpha, beta, and gamma is can be defined using the grid search, but they also provide some values for them that they use, for example, and some constraint that they use for selecting how many depth and width and resolution can be used. Yeah, that's it. This is what I know about. Maybe there are some more insight and thinking about how we define the number of layers, but based on what I know, I use these kind of approaches.
Great, fantastic. I guess we're 7 minutes till noon. Is there anyone having another question? I guess maybe you can elaborate on for this current model, if you want to improve the performance, where would you change in the architecture and so on, and then and how would you and the reasons behind your decisions?
Yeah. So one of the important things is for this image data set that we use is just 28 by 28, but in image and computer vision, what is important is to have image size with a good resolution. For example, if you have, we usually have in our works, we have about 4,000 and 6,000 pixels in images. So applying those kind of images reduce our power to use like batch normalization layers, because we cannot use higher batch numbers. So one of the things before training a network is create some data pre-processing pipeline to find out if you reduce the size of the image, how much information you will lose. For example, if you have 4,000 and 6,000, you can reduce the size, apply a SSIM or maybe a PSNR based on the metrics that you care about, and see how much you can reduce size of the image that you do not lose information and train the system, train the network based on the lower resolution that you do not lose any information based on that. Because if you train a system with a very big images, very large images, I say, it will reduce your power for increasing the batch size. So the batch normalization layer will not be learned. Also, in many of the cases, you cannot train it for long enough time to see the real convergence. So that is the pre-processing part that need to be care of. Also, we can apply some sort of filtering, stuff like that. But usually we like to have raw data inside the images. And if image need to be filtered, maybe we can design some convolution layer with some initialized weight just to do that for us. So we usually do not like to apply some sort of pre-processing to the network, but maybe if it is something out of the scope of that project, for example, you have some images and maybe some labels of annotation of people or text on top of the images. So maybe we can remove those, but we usually like that model works even with those annotation and labels. It give us a robust system. So in terms of that's for pre-processing. But for inside the model, what we can do for improving that is there are some papers talking about max pooling layer that the max pooling layer are not good enough because we are removing some of the features that maybe are important in the network. So there are some other ways that if you want to keep the dimension of the network while we are increasing the output channel size. And for example, like capsule neural network is coming because the main reason was because the max pooling layer was some sort of losing some of the information. So maybe I can remove this max pooling layer and create our network and then flatten the layer and do the same things and get the same performance, and even in some cases get the better performance. But it will increase the size of the network. And one of the other things that we can do is using some sort of convolutional transpose. You can see inside the documentation that I opened that. Let me open that again. If you go to the convolution torch and open this link, so it will show us that when we, for example, apply a transpose convolution, what will happen. So it gives us a better, the convolution are somehow symmetric. So it will give us a better symmetric processing. And also we can increase the dilation based on the network that we have, based on the images that we have. Maybe in some cases, if image is too much large, or maybe the resolution is high, sometimes dilation can help for getting a better performance. And yeah, the changing the like previous session, changing the loss function, the optimizer, stuff like that can be also useful. Yeah, if you have any other idea, I think I don't have any other thing to say. Maybe you have some idea that can bring and we can discuss.
Thank you very much. And we actually have a question by Gagampreet in the chat. Is SSI structure similarity index invariant to image size? If we reduce the image size, then SSI will remain the same or not? What I actually don't know. What's SSI?
Yeah, SSI will not remain same if you reduce the image size. What people usually do is, if we have image, we reduce its size to something smaller, and again retrieve it back to the original size and compare these two for SSIM and see how much information is lost. And we change this size, like from for example, in our case, I mean in Procore, we are working like in 2000 by 6000 images sizes. So we wanna, for example, try if we change the size to 256 by 256, how much information will we lose? So we do this pipeline, see how much SSIM will we get. Then we increase the size, we create a plot, we create a curve, something like this. So we say, for example, if we select 256, we get this type of information loss. If we select 1000 image, we get this kind of information loss. So we will find some way here that we say, okay, we think, for example, 1024 and 1024 is good, and we do not lose information.
Is that how you sort of find the threshold of what's the lowest resolution for training that you want it to be, that without the loss in performance?
Yeah. Based on the images. For example, if images is somehow like structural images, for example, if they are drawing images or stuff like that, so a structural similarity is important. Or maybe in some case of, I worked in endoscopy before, and SSIM was very important in that case too. So maybe the PSNR, maybe SSIM, maybe any other image quality index. There are some deep neural network just for predicting the image quality of images. So maybe you are using those kind of image scoring. Any kind of approaches can be done using those pipeline I've explained, that we reduce the size, return the size to the previous one, and compare the resolution. And that can be helpful before training the network to find out what sizes that we want to use.
Right. Thank you very much. Does anyone else have any other questions? If not, we want to thank Dr. Mehabian again for your wonderful workshops this time and last time. And the next time, as I mentioned before, the seminar will be taking place not this Saturday, but next Saturday on July 16th. For any medical physicists in the audience, if you're going to 8 p.m., we'll see you in Washington. Thank you very much. Bye. Have a good rest of the day. Bye.
Thank you. Bye.